Okay, good morning, everyone. Welcome to the second session of our Bayesian modeling seminar. This, I can do a short introduction of myself. I did PhD in Concordia Physics Department and moved to McGill for a postdoc. So I'm mainly doing neuroimaging for my research, especially on epilepsy, pre-surgical evaluation, etc. So I learned this. I'm not a statistician, so I learned Bayesian like during COVID, and since then I've been using this for my daily practice, and it's been a while. I didn't use any statistical test for my own research. So I select this photo. It's a church. It's a church look like a distribution. I guess there is nothing related to the statistics, but the church it looks like, if I have to assign a shape, it looks like a Laplace distribution, right? And Laplace actually is considered as the one who first discovered Bayesian inference independently. That's a sentence I read from a textbook, and he applied Bayesian in to estimate the ratio of gender of newborn baby in Paris. The binomial. So welcome to the Church of Bayesian, and the talk of mine is gonna be an introduction of toolbox we use in Bayesian workflow. It's a workflow introduced by Habib in the previous session, and I will follow this steps of the workflow, starting from prior choice to posterior sampling, model diagnostic, because roughly a ratio, a proportion of the talk. I hope it sum up to 100. I didn't check, but anyways. And this talk is not about the Wikipedia of Bayesian model toolbox. So there are tons of tools you can find in different programming language. So we were mainly focusing on the STAN ecosystem, which I will mention later what is STAN. And it's not a comparison of frequentist versus Bayesian. We are not statisticians, we are practitioners. So we choose the inference that fits our problem, right? We don't have to use Bayesian for the sake of using it. And the last warning is I will mention some method to like some little bit theory about the toolbox. And I will put a ref at the bottom left. You don't have to take note actually, because the slides will be shared and all the reference, I put a hyperlink, one can click and see what it is. And yeah, so it's better if you go to learn the method if you're really interested from the reference, but not from me, okay? So let's start from the prior. This is the equation of Bayes' theorem. It's basically posterior is proportional to the prior multiplied by the likelihood. So our goal is to estimate posterior by assuming some prior and collecting some data, right? Ideally, we want analytical solution, which means we don't need to compute for a long time. It will be deterministic, and then we don't need this talk anymore. Everything will be solved instantaneously. And this is actually the conjugate prior concept. What is conjugate prior? If you assume a prior which follows a distribution P, and then your likelihood is F distribution, it's different. This prior will be a conjugate prior for the P distribution, which means they have the same form, but they might not have the same parameter, okay? And this is convenient because you will know the form of your posterior once you assume a prior. There are several typical examples of conjugate priors. For instance, beta distribution as prior is conjugate prior for binomial likelihood. and gamma distribution is a conjugate prior for Poisson exponential likelihood, and normal distribution is a conjugate prior for itself. Okay. But in practice, we don't have many conjugate priors, especially when you go for more complicated models, you have multiple parameters. It will be difficult to find a set of conjugate prior for your likelihood, right? So we need numerical solution. And there are several recommendations for the typical prior choice. Starting from flat prior or very wide prior, you can see either you use a uniform distribution or a huge uncertainty in a Gaussian distribution, which actually is not recommended. You might think it's fair because you said nothing, you are not biasing anything, but actually prior is a reflection of what do you know about your research question. If you say, I know nothing, it's barely true because you always know a little bit something, right? And from another perspective, the wider the prior, the higher the uncertainty. And the uncertainty is actually a way to quantify how difficult your problem is. So if you say it's extremely wide, it means it's extremely difficult to study, right? So then you can always incorporate some information you know from your domain knowledge to narrow down your prior, which we call weakly informative prior or generic weakly informative prior. So you see the variance become smaller. Of course, this is arbitrary. We will see with few examples how can you tune this value to be reasonable, right? And in the end, you can set a specific prior. That is informative, you know roughly where the mean stays and you know roughly how much it varies, right? It's again arbitrary. You don't have to think why it's 0.4, 0.2. So I give you some examples. For instance, we all study correlation. You see two things mainly, contrast and correlation in literature, right? Correlation by definition is from -1 to 1. It's not like a Gaussian distribution, or it's not a uniform distribution from negative infinite to positive infinite. So we have a prior distribution called LKG with one parameter eta. So by controlling the eta, you can control the shape of the prior depending on what do you assume. If you put eta equal to 1, it will be almost a uniform distribution, but constrained within -1 to 1, right? And if you increase the theta, it will become narrower and narrower, which will prefer less the extreme correlation values, which will be more realistic because in reality, you barely have a very high correlation between two variables you're studying, right? And then the next one, standard deviation. We want to model, let's say, deviation of individual to a group level or population level effect. You always have standard deviation, which by definition is non-negative. And it also decays fast towards 0 when you increase the variance. Why? Because you don't want your variance to be very high. If it's very high, it means it's extremely difficult to study, right? And the variance can be 0. It means it's 100% certain. It's very ideal, right? So there are several typical distributions for standard deviation. I put two examples here. One is exponential on the left side, and the other is half normal. Half normal is just you cut the normal into half and you choose the right side. Which will give you a non-negative curl. The difference between those two is exponential decays faster than half normal. So if you are not so sure about your variance, you want it to be more conservative, you can choose half normal. It will allow more higher variance exist, right, in the prior. And the last example, imagine you have a parameter, you know from your domain knowledge, 95% of the probability mass is between 2 and 20, and it has to be positive. And how do you find a prior for that? You can use inverse gamma. Inverse gamma has 2 parameters. You can play with that, even do a simulation, and then end up with a distribution that makes sure 95% of the probability mass shown by this red area is from 2 to 20, okay? So now you might wonder, I set a prior, how do I know it is working? How do I know it is objective or not? Because when I use Bayesian and I make a manuscript, the reviewer will ask me, why do you choose this prior? Are you hacking your result because you put the prior? So actually we have a way to assess the prior. It's very simple. You apply your prior to your model, you will get your posterior distribution, right? It's once you know the prior, you know your equation. If you are doing linear regression or whatever logistic regression, you can always get the output. And then you can check your output, how it looks, and compare with what you know. For instance, if you want to be very conservative, you may think my outcome has to be a uniform distribution, and it has no preference on any value. So I'm totally fair and objective. Or you can also check whether your outcome is realistic. For instance, if I'm doing a regression with height and age, gender, and nutrition, I have all my priors for those 3 variables. I can get the distribution of height, right? And then you get height can be around 3 meters, which is not realistic. So it means your prior, by definition, is problematic, right? And then you can tune your prior until you think the outcome is reasonable and it's not preferring any values so that you are not introducing bias. I give you an example with logistic regression. Imagine we are modeling your exam result. It's binarized, so we use logistic regression. It's either good or bad, okay? And there is only one variable, study time. So we'll have one prior for study time. We can use a flat prior and then check what is the probability of exam result being good. What do you expect? You expect it to be uniform from 0 to 1, right? And it doesn't prefer any value within this range, so you get an objective prior. But surprisingly, if you use this flat prior, what you end up with is your probability of good outcome prefers either 0 or 1 in between. And so this prior is not objective as you think. But if you choose a weakly informative prior like here, this normal distribution, the probability of good outcome will be a flat prior. A flat distribution. Right? You don't prefer any value within this range. Then you can always do this computation. You just write down your equation and assign a prior distribution, draw here. But sometimes it's complicated. Let's imagine you do a logistic regression with hierarchical structure, blah, blah. You will have a complex equation to write by yourself. So then with the tool we're gonna mention later, for instance, in BRMS, you define your prior here for standard deviation and slope. And you can set this parameter sample prior to be only such that the model will not sample any posterior, but it will only go a forward direction, giving you a distribution of how your data will look like your outcome will. You don't even need to give any data because here we're not solving the Bayesian equation. We're just pushing forward your model with some known prior, right? And you can also do it in Stan if you want. In the end, in the end of your code, you can define a generated quantity block. Here, I'm just writing the linear regression model here, and you don't define any likelihood, so the stand will your outcome distribution with the priors. So to summarize for the prior section, we cannot simply just imagine our prior is objective or not, right? We need to do some numerical simulation to show that the outcome is fair according to what we know. But don't get misled by me saying flat prior is useless. Actually, flat prior is based on the randomly sampled big data, so that the data will tell you everything and the prior doesn't matter anymore. But in reality, we don't have big data and we don't have randomly sampled data most of the case. So you still need to think about your prior. Now we move to based on this general idea. At that particular program equation here. And in the end, if you want, you can normalize the result. It doesn't matter you normalize it or not. It's because we're estimating the density. It's just relative standard grid for each parameter. With n to the power of 100, you ever, even if you use the most powerful computer. And which has a high probability mass, the region we are interested, right? Shown by this black box. How many samples do we have? 9. But how many samples do we use for the whole sampler? 81. So for this case, the efficiency is just 1/9. And here I give you a more general summary. If you imagine you are doing a 1D 1D Gaussian, let's say, and this is the region you prefer to sample, and you do an evenly distributed grid, it will be 1/3, the efficiency. And in the 2D case, if you care mostly here, it will be 1/9. And in 3D, it will be 1/27. So the efficiency will decrease and decrease. So we want a multiplier, like Dr. Strange. He can calculate in seconds. There is 1 out of 14 million chance, right? So what is this sampler? It's called Markov chain Monte Carlo. It's an algorithm. I can explain you with a simple example. For instance, I want to know the distribution of people in this building. What I will do is I count how many people do we have in this room. And then I make a random proposal. I will go to the 4th floor, some room for, I don't know, 4.100. And I check how many people in that room. And then I compare. If there are more people, I will stay there. Otherwise, I stay in the current room. And then I make a new proposal. And then you will see me running around in this building for a whole day. And after all, if you check how long do I stay in each room, it will be proportional to the distribution of the people in this building. This is a concept of Markov chain. So I am a chain because I'm working one location to another location, right? So my trace is a chain. And to be more like formal, this is a random process. Each new state depends only on the current states, right? I will only check how many people do we have in this room. And then the proportion of time the Markov chain stays in any given region converges to the probability mass of the target distribution. So this is a general concept of MCMC. So we move to our first sampler for MCMC, which is called Metropolis Histine. People also call it random walker. It's really like randomly walking in the target distribution. Here is one example. We have a target distribution. Of course, we are hacking because I show you what is a target distribution, but the sampler does not know. This target distribution is a 2D Gaussian shown by this bluish color, right? The center, the high probability mass is around the center, okay? And what do you do is, as I said, for this distribution of people in the building example, you initiate the starting point randomly anywhere in this 2D space, and you will get a set of parameter theta. So So the chain will spend more time in the high density regions, okay? And then you will converge and you will get your target distribution. For instance, here, every single black dot is one sample. And the arrow is just a proposal. And the direction is showing you where you propose to jump. And it's random, okay? And it can be longer, it can be narrower, shorter. So if it's shorter, it means you just jump to the neighbor regions, right? And the red arrows shows rejected proposal. The green ones is accepted. So you only sample when you accept, and you reject. When you see a red arrow, it will not sample, but it will go back to the original location. So what will happen, you already see here, is the acceptance ratio is low, which means you will waste a lot of computation for those red proposals because you are not sampling anything, just doing the computation, right? And you will also have low efficiency because each new state depends on the current state. So the chain itself, by definition, has some autocorrelation. So if you check all the samples you get, because of this autocorrelation, the effective independent number of samples will be low, okay? And you will also have low efficiency for those regions that has low probability mass, because the chain will have a low chance to go there, right? So before we move to a more effective sample, I'd like to introduce you this concept, which is important but challenging to understand. So it starts with this claim or comparison between combined parameters that maximize your posterior probability. So it's a long sentence. What does it mean? It's actually your mode of the distribution, right? You have, let's say, n parameters. That mode is a combination of n particular values that maximize your posterior density. Okay, imagine a 3D Gaussian. It will be a peak over there. Versus the high probability mass of the joint distribution. We want the high probability mass. That's the reason we care, because it's more likely to happen, right? We want to sample that area. So is it true that if you go to the mode, you will sample the high probability region? Actually, it's wrong. And it will become far and far to the mode when you increase the dimensionality of your problem. So I give you an example in multi-Gaussian case. What I'm doing is, imagine I have a 1D Gaussian. I just randomly draw 1,000 samples, and I calculate what is the distance of each sample to the mode. Let's say the mode is 0 for all the n-dimensional Gaussians. So the distance will be very simple to calculate, right? And I will draw the distribution of the distance to the mode what will happen is for 1D Gaussian, you see most of the samples are close to the mode. So this is a distance to the mode, okay? The mode represents the highest posterior probability density, okay? It's a peak of your posterior. And when I increase the dimensionality, it will become far and far to the mode. What does it mean? It means actually the region you want to sample, which contains the high probability mass, will become far and far to the mode, okay? So it's not just simply do a gradient descent and go to the mode and then sample around, which will not give you what you want. So there are some theory to explain this concept, concentration of measure. Let's imagine we use a spherical view of our parameter space. So your parameter is like a sphere space, and I define some boundary. Imagine my mode is here or here or here, okay? And I move a unit distance delta, and I'll check what is the volume inside and outside this boundary. In 1D, it will be equal. In 2D, the area here and here will be different, and this one will become larger than this. And in 3D, the volume here will be much larger than the volume inside. Imagine this is your mode. If you move a unit distance every time, far and far from the mode, this volume will grow bigger and bigger and bigger. So people call in high-dimensional space, it's a lonely space, right? If you are far from the mode, it will be very far from to your neighbors. And what is this volume? This volume is in the equation of Bayesian theorem. So here we're just estimating the expectation of your posterior, right? This is your parameter. This is the parameter. This is your density function of the parameter. And this is just the function of your model, like a linear equation or whatever. And this dq is the volume. It will increase dramatically when you move far from the mode, okay? And the density function, we know at the mode, it will have the highest value, so it will decrease. But what we want is the integer. In the end, what you get is this dark red distribution, and you want to sample this distribution, which is represented by the gray box. And there is a concept called typical set. So typical set is the region we want to sample in your posterior. Okay? Any questions? Okay, so now we move to another example. So here, my typical set is this blue region. It's the 2D donut distribution. Okay, I want to sample this distribution, which will be more challenging than the 2D Gaussian case. And I'm still using Metropolis Hastings random walk. So here you see it's slow, it's much clearer to see. There are a lot of rejections here. I make a proposal, I reject it. So most of them are rejected because it's quite difficult to stay in the typical set. It will go to this white area and the density is low, so it will decide to stay here, right? So in this case, it will be even more low efficiency and low acceptance rate. And this is another example. Imagine we are sampling a 2D Gaussian with some correlation here, theta 1 and theta 2. With 200 samples, you are drawing like, we start from here, we jump here, here, and it will surge and finally it goes inside, but it will wander a bit and sometimes it go outside. But with 200 samples, you are not covering the whole distribution, right? So you need more sample, which means more computation. In this case, 1,000 draws will give you roughly a good coverage of the 2D distribution. And now we move to another more advanced sampler, which is called Gibbs sampling. And it's actually, there is a famous software in Bayesian history called bugs. It's funny to call software bugs. It's Bayesian inference using Gibbs sampling, right? And it's actually a special case of metropolis Hastings. Remember, we talked about conjugate priors previously. The convenience of conjugate prior is once you know it's a conjugate prior, you know your posterior will have the same distribution as your prior. So you will roughly know, you will not roughly know, you will know how to compute that posterior more easily, right? So in this case, you can have acceptance rate of 1 because you know that you can set the conjugate prior and your proposal will always stay in a higher probability mass region. But one thing you notice here is the chain is always moving one direction at one time. It's either horizontal or vertical because you have two parameters. But the conjugate prior is set for each parameters one by one by fixing the others, okay? And this is an example for Gibbs sampling of a 2D Gaussian we saw before. With 200 draws, you can already see it's doing a fairly good job comparing to the random walk sample. Okay, so I guess we can have a break, no? Yeah, I will continue. But there are problems for Gibbs sampling. First of all, it requires you to divide your joint distribution into subset such that you will have conjugate priors, right? Why we do this? Because imagine you have conjugate prior for your whole joint distribution, then you don't need to sample anymore. You have an analytical solution. So in reality, you don't. So you need some mathematical skills to divide your equation into several subsets, which is already hard. And also we see this jumping either horizontal or vertical, right? So this means you are sampling actually one parameter out of time. You are updating, let's say, one parameter one time. This is problematic from the theory of concentration of measure because what we know is when we have high dimensional space, we are not just, we don't care just one parameter, but the combination. And if you move only one parameter to the higher probability mass region, particular to that parameter, you are not guaranteed to move to the high probability region for the combination of all. So in theory, if you have a high dimensional model, this sampler will not work very well. So how do we explore the typical set more efficiently? This is an analogy people often use to explain the sampler we are going to mention is imagine you want to sample this U shape, which is your posterior distribution. And you can use gravity. So you can glide through the whole distribution and the gravity will allow you to stay always in your typical set. And then you just need to sample at a certain time. Like you can sample here, here, and you always stay in the typical set. And the gravity in parameter space is gradient, right? You can compute the gradient for all the points in your parameter space, and you got the gradient. And then what you are doing is similar to launching a satellite. You need to add an auxiliary momentum such that your sampler will be sent to the typical set, and it will stay on that typical set, which is like the orbit of Earth, and it will not crash because you particularly tune how much momentum energy you're gonna add, right? So it will stay in this set, and then it will glide through a bit and do a sample. So this is one example of this type of sampler. So here the blue trace is not sampling yet, it's just exploring the typical set. As you can see, it always stays in the region, okay? It can be different shape, but it always stays. So it's like gliding through, following the gravity. And then it will wait a little bit and make a sample. But why you see two traces here? It's actually to avoid the case like you make a U-turn and you go back to the original point, you make a sample. That will not be efficient. But you may say it's very rare to have exact same location, right? But you may end up with some near region, which is also not cool because you want your sample to be far to each other every time so that they are not correlated that much. So by doing two directions, you can make sure that when they meet, you have a chance to make a U-turn, right? And then you say, I will stop earlier, such that you will jump to a location that will not make a U-turn. For instance, in this case, you see it will explore, and there is no sample made. But once they meet, they will say, okay, I will jump to this location before I got these two traces meet each other, right? This will make sure your samples are far from each other and increasing the effective number of samples. This is the fast version of the sampler. So you see you always, not always, but most of the time you see the green arrow, which means the sample is accepted. So it's an indication of high efficiency, and the sampler is evenly distributed, those black dots, across this typical set, right? You are not missing some regions, or you are not biasing some regions with small samples. So here is the side-by-side comparison of two samplers. Left side, you have a metropolis histine or random walk sampler. Right side, you have this non-U-turn sampler, okay? So you see the other one is much faster and much more efficient. And this one actually it struggles. Some region it cannot sample with a small number of draws. So if you wait long enough, this one will also work. It will converge, but you need a lot of computation. Okay.
With the arrow, the dark blue arrow, the arrow space.
Yeah, the blue region is the high probability mass region. It represents where you want to sample. Okay.
But why in the middle of the circle
it's a hypothetical case. It's just to have some challenging to the samples, right? You don't want to go to the middle because the middle is like you don't have a higher probability there.
It's the typical set.
The typical set is the blue region. It's this donut.
Yeah, I mean, why is it?
Well, it's just an example to show to have some challenge for the samplers, right? It can be any shape. Actually, if you check your model with multiple variables, we have some example later. The geometry of your posterior is, let's to be precise, joined posterior distribution. It's joined because you have multiple parameters. So it's a complex geometry. It's not a sphere, it's not a ball, or whatever. It's always complex.
So you can like predefine it.
You don't predefine. Here we show you the distribution just to you can assess visually how the sampler works, right? Under the hood, the sampler does not know. Or in other words, I can take off the blue donut and I show you the sampler. It's going like a rain. And in the end, I superimpose the ground truth. And you will say, wow, it's really working in this region, okay? So distribution. And actually, you can easily make this donut shape by defining this theta 1 and theta 2 like this marginal distribution, right? In the middle, you have low probability On the side, you have high, and then when you combine them, you will have this donut shape. Okay.
So you define the two parameters distribution and you got the donut.
Yes, it's predefined. It's something like a hypothetical example. Actually, not me. I got this example from someone else on GitHub. Okay. So in practice, you don't do this by yourself, right? You have some tool to use. This is a tool we're gonna mention today is called STAN. There are multiple explanations of why Stan is called Stan, but it's definitely not Stan Lee from Marvels, right? It's officially on Stan website it says Stan is a state-of-art platform for statistical modeling and high-performance statistical computation. Some people say it's named after this scientist, Stanislaw Ulam, who invented MCMC algorithm in the Manhattan Project. Okay, and the STAN team is diverse. It consists of statisticians, physicists, computer scientists, engineers, and practitioners. So they have different perspective on this sampling business. So they care the practitioner user-friendly, and they care the performance of the sampling to make it most efficient, etc. I remember there was maybe a talk I heard. They have some comparison of this type of sampling across different softwares, and Stan is one of the most efficient one. Not one, it's the top one efficient model. And Stan is not only fast to sample your posterior. Actually, it's designed to crush your confidence with all the warnings and errors you will get. So the first time you play with Stan, you will have a lot of trouble to write a code that works. Once the code works, you think, okay, I will get my posterior sample. Not really. Most of the time, you get a lot of warning telling you there's some issue of your sampling, etc. This will be the part for the model diagnostic we'll mention later. Okay. And here is a side note. Why it's called Markov chain Monte Carlo is Ulam's uncle used to gamble in Monte Carlo, so they named it together with Metropolis. This is a Metropolis system, Metropolis. They published the first paper on MCMC algorithm. Okay. So there are two options to write, like to use Stan in practice. One is you write your Stan code, and you have pretty much all the programming language that is available to write a Stan. You can not only write, you can compile, because Stan itself is a C, it's a C, it's based on C, but you can always compile the model. You write, you compile, and you can run the model within your R environment or Python if you want, or Julia. MATLAB also works, but it seems it's not so supported anymore. Yeah, and usually for me, I use CMD Stan or R Stan. And here is an example of how Stan code looks like. It's just different chunks. You define your data. So the model here I'm doing is solving the fMRI GLM model to estimate the response of the brain. You have multiple variables in your linear regression, etc. So you see, you have to explicitly define everything, like the dimensionality, the boundary, the variable types, everything you have to declare. This is the data part. And then if you want to do some transformation of the data within the model, let's say here I'm doing a QR decomposition of my design matrix before I put into the linear regression, you have to put it in the transformed data chunk. And then you have a chunk for all your parameters. Again, you need to declare what is the type of the variable. Is it a real value? Is it a vector, etc.? What is the dimension? And in the end, you write your model with your priors written and the likelihood function, okay? And then once you write this model, you compare and you can feed the data and do the samples, which looks like complicated because you really have to figure out all of them precisely. Once you make one mistake, even you declare the wrong type of variable, it might give you an error. But luckily, we have this tool from the Stan team. It's a website. Like you can check what are the available functions here, right? It's a list of all the functions. Sometimes you don't have the function you want. For instance, when I want to do a convolution, they don't have this function, so I have to write my own function. Or FFT, it was not available, but recently available. So you can also put your code here. You just copy paste here, and then we'll do a check of all the errors and give you suggestions so that you can learn by checking this your draft, right? It can also do the automatic format, like add indent and do a new line to make your code more readable. So before we move to the next option, I will show you some example with this tool called Stan Playground. This is just a tool for, for beginners to play with Stan, see how it looks and so on. It's also from Stan group. What I will do is I click, sorry. Oh, someone, sorry. Stan Playground. Okay, so let's do a linear regression. This is what I showed you here. You have your data. This is a dimension of the data, and then X and Y. Your parameter is just alpha being the intercept, beta slope, and sigma, which is the error, right? And you write your likelihood function here, which is a normal distribution. You can put data in this JSON format, just copy paste here, and you define how many chains do you want to sample the posterior. And there is a parameter called warm up. It's just to let the chain explore the typical set first of all, because it has some parameters to tune, like the steps of the jump and the length, etc. So it will decide an optimal parameter for the sampler of your particular posterior distribution. And then it will not use those samples, but draw the new samples, which will be your real posterior distribution. So for instance, here, I have 1,000 samples, 4 chains, which will give me 4,000 samples in total. This is a typical choice for those sampling parameters if you want. Okay, and I can compile the model here, and then I can run. So it finished very fast because it's just a linear regression, right? And you have your draws here, each parameter, the values, the summary, and the explanation of each variable. And you can even see the histogram of your intercept and your slope, right? We can also check some diagnostic, which I will explain you later, the trace plot of each chain. So here you just have the value drawn from each sample, and you have 4 chains, and it's just going randomly up and down, and here is just the number of draws, okay? So in total, you'll have 4,000 draws. We can go back to the second option, which will make your life much easier. You don't have to write that long Stan code chunk, and you will use some high-level modeling interface. And I will introduce you mainly this very popular tool called BRMS. It's also from Stan team, right? But this has to work with R. You have another similar version in Python. We can talk later. If you go to their website, you will have detailed explanations how to install, giving you some example and even some plot, which we'll mention later, right? So how it works, how it make your life easier is it will use this syntax. Probably some of you are familiar with this. When you do like a classic regression analysis, you can have this syntax, for instance, for random group intercept. One is intercept, and you put here as your group. And for some nested hierarchical structure, meaning block is nested within set, right? And this is a corresponding equation if you want. So this is the part you have to write in STEM by yourself, but on the right-hand side, you just write this syntax in BRMS. But you have to know your syntax is correct, is what you want, right? And there is another tool that is convenient. Imagine you write this syntax first. You don't know the equation. It can translate you to this equation, which is convenient in two senses. One, you can verify whether the syntax you write is the model you want. The other thing is, imagine you want to write the equation in your manuscript. It will be convenient also, right? But actually, most of the people, when they learn regression, they don't write this equation. People mostly start with this. That's why BRMS is popular. Because for frequency statistics, people do frequency inference, they can easily switch to Bayesian because you're gonna use a similar syntax. It's just a different way of sampling. Okay, I think we can have a break and we will do the diagnostic. Okay, I'm muted. So before we start this diagnostic, there was a question during the break, like what's the difference between optimization and this sampling, right? Optimization, like in machine learning, you are looking for one point that maximize your loss function, right? But here we are exploring the whole distribution. So it's multiple samples, okay? But instead, you can set your sampler to do optimization, which will give you the, let's say, maximum likelihood or whatever or you can do some risk constraints to have one point solution. It's possible instead. So the convenience is once or just a maximum likelihood, okay? And there are different options like optimizer setups you can play with instead. Okay, go back to our diagnostic. So now you have your prior, you fit your model, you got the posterior. How do you know your samples are correct, or how do you know it explored the typical set very well? Represent your target distribution. There are several what we call diagnostic of the sampling. Like the most common concept you also hear from machine learning is convergence, right? Do I get the convergence of my sampling? Here I showed you previously the trace plot of each chain. Imagine I have 4 chains and I randomly start at one location in this high dimensional space. And then I start sample, right? Here I got 2,500 samples. So I can plot the trace of each chain and then visualize it. And what you see here is each chain is going up and down and explore the range of this theta. And also 4 chains, you don't differentiate them very well. They mix very well. So it's an indication of convergence. And here is an example that chains do not converge. Like for instance, this green chain, it it's only sampling mostly the positive part of the parameter, right? And the red one is mainly sampling the negative values. You can also see the chains, they don't mix together. So it's like one chain is exploring some part, the other is doing the other part. And you might wonder, why don't I just combine full of them? But how do you know each of them is exploring like a subset that when you merge, you will have the whole set? You don't know, right? Usually this is an indication that you have a problem of your sampling, which will not go through the whole distribution everywhere. What you want is no matter where you start the chain, you want it fully explore the area, right? If we go back to the analogy, like no matter where I start my computation of people in the room in this building, it shouldn't influence the final distribution I estimated, right? And you can have some numerical evaluation by computing the ratio of between chain variance and within chain variance. And this ratio will give you a quantification of your convergence. And usually you have a threshold smaller than 1.05, and you can even plot. So here, each bar is one parameter, and it's R hat value. And you can color code by different threshold. This threshold is really arbitrary. It changed from like, even if you look different resources, it changed a bit. Sometimes people use 0.1.05, sometimes 1.1, but as long as you are checking this. And the other one is what we talk about, the sampling efficiency. If you want to have a high number of independent samples, because the independent sample is the sample that represents what we call Monte Carlo error of this whole sampling business. And it can be computed by a ratio of total number of sample and the equation related to the autocorrelation of the chain. Remember, we talked the chain has some autocorrelation. Like here, we are checking for one parameter in one column, and each row is one chain, right? You can see the autocorrelation of the chain, and then you can estimate how many independent samples do I have out of all the samples of the chain. And you can either use the ratio of effective number of sample over the total, or you just compute independent samples right away. And usually you want more than 400. This 400 is related to the sampling error, which if you look for textbook is roughly 0.5 error, sorry, 5% error of the sampling. Of course, you can have more. And then there is an important concept called divergence. So imagine you have this distribution 2D, okay? Theta 1 and theta 2. It looks like this weird shape. Actually, you will find out it's not weird at all. It's also related to your question about the donut stuff. So the region here, imagine I'm sampling here. To go inside, I need a small movement, small jump. If I jump very far, I will miss this region, right? But if I set the jump to be very small, I can go inside. And then I have a chance to be trapped because the jump is small. I will spend a lot of time until I get out from this region. So this is very tricky problem. It's related to your model structure, usually caused by a correlation of two parameters. When you have correlation of two parameters, you will have this shape. And this shape even have a name called Neil's funnel, named after Neil at this paper. He's a professor from Toronto University, okay, yeah, in computer science, I think. So here I'm just marking the divergence at each point, meaning the chain got some problem with this divergence issue. It's mainly within this funnel. And how the stem knows this divergence happens is, remember we have this analogy in physics, like you have a momentum energy, and then the chain will launch to the typical set. It will do this sampling. It has also some kinetic energy, so you can always compute the total energy. And when the total energy goes to infinite, it's an indicator of the chain that flies off the track. So that's the time you record this position, say, I got some issue and the distribution looks bumpy here. So I record it and be careful. And often when you do a STEM model, you finish the sampling, it will have warning telling you there are 20 divergence in one, which is a warning. It doesn't mean your sample is totally wrong, right? You can still estimate your posterior, but it means it's maybe you didn't go inside this funnel region. You missed it. Maybe you trapped there. So it's a time to either redefine your model or play with the parameter of the sampler to make it go inside. And then the ultimate goal is to not have a divergence, right? For instance, one trick to play with this issue is will be the same, but you reparameterize, and then you will remove this type of correlation to make the geometry simpler to sample. And this actually happens mostly, not mostly, quite often in hierarchical model. Often you do a hierarchical model, or in other words, maybe you are familiar with level. I have an individual here defined by a normal distribution mu and tau. And this, by definition, will introduce some correlation between theta and mu, and theta and tau. Inherently, because you define it's coming from the population level, right? And if we check like this divergence by plotting the paired distributions or scatter plot of each parameter from your posterior, you will see those divergence happens, right? And this is a time to reparameterize the model or tune the sampling parameters to avoid this issue. It's also an indication of the complexity of your model, okay? And if we go back to this issue, like except for hierarchical model, sometimes you have multiple variables. And the correlation or relation very complex. So here I only have 3 parameters. If I look just in 2D, like a pair of 2 of them, you will think, okay, the distribution looks not that complicated. It's like flat, but focus on this region. And now I show you the 3D view of this distribution. It looks like this. It is actually a thin slice, and it has this curvature. So what you are doing in your sampling is this distribution. So now you see the complexity, and this is just 3 parameters, okay? And this will have this funnel and will make your sampling difficult. So we need the diagnostic to know whether we sample this fairly well, right? And for diagnostics, usually you can use this tool called Bayes plot. Once you fit the model, you can give the model to the function, and it will do all kinds of diagnostic for you, either visualized or a numerical or quantified assessment. For instance, I fit a model, I give the posterior to the function, and I will tell the function I want these 2 parameters. So it will show me the trace plot we showed before. Here you see a convergence. Like you can have the 4 chains. This is parameter-wise, right? Each row you have 1 parameter. And you can also give your posterior to show the paired plot of 2 parameters and the indication of divergence here by a red dot. Okay, so there are other diagnostics matrix I wouldn't cover in this talk because it will be more like complicated related to this physics analogy of HMC, but fitting or BRMS, you will check the diagnostic. The convenience is sometimes you fit a model, you don't get any error and any warning message, which usually is a good indication that you are safe, because especially when you do BRMS, it will show you the warning if you have divergence, etc. Okay, and in the end of the fitting summary, you see those effective number of samples, etc. So now let's say your diagnostic shows your sampling is not pathological, so it behaves very well. You can assume you sampled your posterior quite well, and then you need to interpret your model, right? Like it's time to show the result. The easiest way to show the result, of course, is you show the posterior distribution, as we mentioned in the first session. You have a distribution, you can extract like maximum A posterior, like the peak or the rope or whatever parameters you want. And then in this case, you can use this tool called tidy Bayes. It also takes the output from BRMS, and then you can plot your posterior for each parameter with different styles you prefer, right? Like here you can do a density plot or a dot interval plot or just a bar. And here you can have some uncertainty range. And like one thing for Bayesian, when you fit a curve, let's say, you will not end up with just one curve with arrow bar. What you will get is one sample is one particular curve. So here you can even show all those curves from your fitting. Imagine you did 1,000 samples, you will have 1,000 curves here, and you can see how they look like. And you have all kinds of different styles here which you could choose. And the author is quite good at data visualization in general. He has several publications on different data visualization. And you can also learn some data visualization skills from this well-documented toolbox, right? But sometimes you don't want to just interpret your parameters because some parameters are not easy to understand. For instance, you do a logistic regression. What is the meaning of that parameter? Like let's say a slope for a continuous variable. It's by definition log odds. Okay. And then how do you report and explain to people, this is my log odds of this variable? Of course, you can take an exponential and you will get odds, which will be easier to understand. But in the end, what we want is a more intuitive understanding of the model. So what we do is we use this concept called marginal effect. Is we all learn from probably science course in primary school is you want to know the effect of one variable, you fix all the others, right? And then you change this variable only, and you check what is the outcome, how the outcome change, so that you learn the effect of that variable, which is the most intuitive way to understand your effect, which is also related to your research question. It's like you have a mixer here. Some are continuous variable. You can tune one of them, but fix all the others, and then you check how the sound sounds like. Or you keep all the others fixed, and you change the dial, which is a categorical variable who has several levels. Dial, right? And this is the technique we combine marginal effect in Bayesian session with what we call posterior predictive simulation. It's a long-term. Your model fit, you know the parameter distribution, right? So now you can give any value. As if you are doing prediction, like in machine learning, you give a new value or existing value and see what is the outcome, right? And this, because we have posterior, so it's called posterior predictive simulation. And we will have not only one value. Once you fit one data value to the model, you end up with a distribution of the outcome. And that distribution not only tell you what is the mean of my prediction, but also the uncertainty, okay? That's the benefit. And then there are different ways of summarizing this marginalized effect. You can go to Andrew, his blog. He has a very nice summary. I can go over with you quickly. For instance, I can do the simplest way. Here, one row is one particular combination of data, okay? One column is one variable. Now I have my model already fit, I know the parameter. I can fit this original data in the model. I will end up with one distribution of that particular data for the outcome. And then I can average all of them, which is marginalizing, and then I will get the distribution of how the outcome looks considering all my data, right? And if you care the effect of a continuous variable, for instance, let's say age, you fit all your data to the model, you get the distribution of the general effect, and then you change the age by, let's say, 5 years old. You just add 5 to the age column, and you fix all the others the same. You'll get another distribution, which is a distribution you can compare with the original data. And then the difference will tell you what is the effect of age by adding 5 years old on the outcome. And it's again a distribution, not only giving you the mean of the effect, but also the uncertainty, right? And for categorical variable, for instance, you have different levels. You can also have a posterior distribution for each level, and you can compute the contrast. And the contrast will give you the difference between two levels in terms of the final effect on the outcome. And the convenience of Bayesian is each sample is paired for all the parameters, which means you do a subtraction, the subtraction is also paired. So you don't need to redo your fitting. Let's say you just model the difference and then you redo, you don't. You can, once you get the posterior, as long as you don't shuffle the order of the sample, you will always get paired. And then the computation is always paired. And you will get, for instance, you can add weight to the contrast. You see, I give more weights to this level and less weight to another level. You do a contrast or you do combination, whatever. You can even apply to an equation, transform to another type of effect, right? And one simple marginal effect is you average your data. Like for all the continuous variables you average, you get the mean, represent the population mean, right? And then for categorical variables, you select the most frequent one. So you end up with only one particular set of data. And through it in the model, you'll get a distribution representing the general effect in population level, right? Of course, you can select some specific values that you think represent a particular group that you care. For instance, the age of 30, education level at this and blah, blah, which country and so on. And then you will get the effect of that particular data. So it will make your interpretation of the model more intuitively because that's all you care about, the effects of each variable, right? Instead of just checking the raw parameter value. So in practice, you can do this by yourself because you know your model, you can apply the data, and then you just need to be careful when you average, you make sure it's averaging within the category you want. or you are adding this small change of a continuous variable in the correct way. But we do have a package called marginal effect size, for which you can use your Bayesian model fitting or even your maximum likelihood fitting to this toolbox, and you will specify which variables you care and what type of marginal effect you want. You can do, for instance, compare slope like continuous variable. It's the effect, it's the slope, right? You increase a continuous variable by a certain amount. What is the increase of your final outcome? And this will give you all those summaries. So that's diagnostic. Oh, sorry. I listed a lot of metrics here. Basically, model comparison, you can separate into several categories. Like if you care the goodness of fit, for instance, you can use classic R square, or you have a Bayesian version of R square, or maybe you care generalizability. In other words, the predictability or whatever you call it. You can use things like WAIC or leave one out cross validation or k-fold cross validation, etc. Or you can, if you care evidence, you can have Bayes factor like Habib explained last time. Or if you care goodness of fit, a balance between goodness of fit and complexity of your model, you have this classic AIC, BIC, etc. Each of them, you will have multiple tools to compute. Like if you fit using BRMS, you can directly compute R square or leaf validation. This is just your fit. You fit into the function, it will compute it for you. And if you want some easy comparison, you can use this performance model package from EasyStats ecosystem. This is not only for things. Regression model using R-star-norm is a similar package as BRMS. I also use this syntax to simplify the model following specification. And then you come this function. It will give you a summary, like a monster summary with all types of evaluation metrics, right? And if you want, you can even rank the model by giving rank equal to true. So it will rank all the models and put the best performance on top. Well, of course, this ranking is considering all the metrics we listed here, right? And it will give you a normalized score. For the top one, it will be 100%, and then the second one will be lower and lower, but they don't sum up to 100. It's just top one has 100. But of course, if you want to prioritize, let's say, generalizability, you can assess by yourself. So the idea of model comparison is you need to know what is your criteria, right? You don't want to just use this default stuff and get a model says this is the best, because even if it says it's the best, how do you explain it's best in which sense, right? And then you need to explain all those variables, which will be complicated. Usually, I would suggest to choose one matrix for goodness of fit, one matrix for generalizability. So I have a good balance of overfitting and prediction, right? And you can even, let's say, I put a plot before this whole code. It will give me a spider-web plot showing each matrix on each axis. And then it's normalized in a way that the highest performance model always have this highest value on the corresponding corresponding matrix, and then area within the spider web. Which one is the best? Okay. And then in Bayesian, when we assess generalizability, there is this famous toolbox called LU. It's leave one out cross validation. What do you do with leave one out cross validation is you fit your model with by removing one data, right? And then you check how well you can predict that data. And then you repeat. And imagine you have 1,000 data, you will fit 1,000 times, which will be time consuming, especially for Bayesian model, it's almost impossible. But we have this nice method which can approximate the leave one out validation performance by fitting the model only once. So you fit the model with your full data only once, and then it will estimate you what is the leave one out cross validation matrix without refitting it from this package. Okay, so if you have a BRMF model fitted already, you throw this into a loop. It will do the and also do k-false cross validation, etc. Right? Yes.
How does it do that?
Well, behind that, it's using something called parietal smooth importance sampling. It's like a very complicated statistical technology. Yeah, but they showed very well in literature that yeah. And that's related to your question. If you want to know the detail of how it's done, this is the author of Lu package, who's a computer science professor in Oulu University in Finland. He has a very nice blog. If you go there, you have all those FAQs about cross-validation, etc. He explains all the metrics and how do you compare, what is the criteria of the value, because I didn't go deep, like, because the value, to understand the value itself, the matrix, it takes time. For instance, here in Lu, what we care is what we call expected ELPD, expected log probability density. So you have your posterior estimated, you put the new data, and it will tell you where it is, how likely it is, which is just one vertical line on the distribution, right? And that's the density. You take a log, and you want that density to be high, because then it means it's more likely to predict this data, right? And then you sum up all this value for all the leave one out. You will have a matrix, this ELPD, and you can compare with all the other models. But it will be very complicated to understand, like, within a few minutes. So that's why I put the resources here. If you're interested, you can go and take a look there. But the idea of model comparison is you compare several models to understand some effect. Sometimes you remove one variable from the model of the importance of this variable in your model. So you learn something by doing model comparison. Bayesian workflow is when you do model comparison, they say you always fit multiple models, and by doing comparison, you learn. Actually, you will be always surprised. You will learn something new related to your question, and maybe you go back to make another model based on your update and your understanding from the model comparison, and that will be your final model to interpret the effect, right? Okay, so before we finish, I have some blah, blah, blah. It's a summary of my talk. For me, the Bayesian workflow you see we went through, you have to set prior, you have to check your model fitting your equation, you compare the model, you learn the effect, you go back, you tune your structure, and maybe you end up with a better model, or you can do a model like Bayesian model average. You average several models to have a better performance in terms of what you want. But you may notice it's actually not data-driven, hypothesis-driven. That's the fundamental of science. You make a hypothesis. Why it's a truly implementation? Because you specify everything. You explicitly define everything, which you don't do. The time you do Bayesian, you will realize you never cared the prior in your linear regression before. What is the prior of your maximum likelihood estimation, or your least square estimation of linear regression? Most better, right? But when you do your least square solution, you interpret that there is an underlying assumption which says your prior is uniform. But is it true? Do you really think your prior is uniform, right? And then it's beautiful, but it takes a long time. First of all, to appreciate it. Just to appreciate Bayesian is already difficult. Most of the time you hear people say Bayesian is, we will say it's complex, and why am I doing this? And it will take a long time to learn. And for me, learning Bayesian is not only about statistics. It's also like a training of rational minds, because again, you care more on your research question, because without specifying everything, you cannot go one step, even starting from prior, right? So it forces you to think about, what do I know already? The question I care, right? And also be aware of the acceptance of Bayesian in your research field, which means if you spend a lot of time learning this and you made a manuscript, and most of the reviewers, they don't understand, which is the reality. But for some field, Bayesian is a default go-to. Some field, not really. So you need to assess that before you really want to spend some time. I got this warning when I started. I really appreciate this warning. So even if it sounds a little bit negative, I prefer to say it here. But I don't regret to learn this whole thing. And if you decided to explore the Bayesian, I recommend you just go to the STAN committee. You have all the learning resources. Not everybody, most of the developers, they have blog, they write case studies, and the STAN documentation is very well written. And they have forum, you can ask questions and you get expert to reply. And in the end, please don't forget about your domain research. Again, we are not statisticians, so we don't care the war of statistics, who win frequency versus Bayesian. So if you find one fit better to your questions, just use it. Don't use it Bayesian for the sake of using it, right? And in the end, I will share you some learning resources. This is how I learned since COVID. Like, you have this nice book called an practitioner or application. He's not like statistician, but he's extremely good on explaining complex things. And he is explaining from the application point of view. And this is quite a popular statistic book. And then if you want some hardcore Bayesian, you go to this one, BDA. Usually you see people say BDA 3, it means Bayesian data analysis third version. This is how people refer to this book, written by Andrew Gelman, who is a statistician and professor in Columbia University. And this, you will have all the equations and theories behind the Monte Carlo sampling error and the different models, different family of distributions, etc. And then they also have this book more for practitioners, Regression and Other Stories, written by Andrew Gilman. And this is like more practical. It's not based on BRMS, but R-STAN-ARM. It's the same thing. Like you use the syntax we mentioned. Maybe Albay will explain this. We'll use this toolbox later in the next session. But you have all the regressions starting from the simplest one and to go multi-level, etc. And you will learn a lot of statistics from this book. It will also do a comparison between frequency and Bayesian. You will find you actually, even if you will not end up with using Bayesian, you will understand much better what you are doing with significant tests, etc. And for this rethinking book, you also have a version written in BRMS. It's like all the examples in the book is written in BRMS. So you can follow the book and follow this. It's digital, it's free. And you can run all the examples to learn and go through the whole book. And you have blogs from the developer, Michael Bentecourt, who explains all the hardcore physics or math behind. He's a core developer of STAN. You see some figures I referred, like the concentration of measure, etc. And he shares his writing for free. Like he's preparing a book on all those Bayesian techniques. And you have Aki, we mentioned the developer of Lu. He's also a STAN developer. He has his own course in Waterloo University. You can find it, all the videos and course material on GitHub for free. And you have blog from Andrew Goldman for statistics, and they write stories. Sometimes they criticize the literature. Like you can even send the paper that you wonder about the statistical issue, and maybe he can comment. Like in FMI field, we have this famous cluster failure, like multiple comparison issue, that paper on PNS 2014, it went famous, and someone sent to him, he commented a bit, which is quite interesting if you take a look. And Richard McLaren himself has a YouTube channel. He uploads his course on rethinking book every year since 2019, or 15 actually. And this is a course in Max Planck, and you can follow this course and learn all those stuff. That's how I started, by watching this. And in the end, you have a podcast called Learning Bayesian Statistics. It's from a developer in another universe or ecosystem. On the Python side, you have a package called PyMC, which does a similar thing as STAN. And one of the developers, they have this podcast. It's been like 145 or something. I didn't listen recently, but there are 100 episodes. You will hear some episodes from those people and learn different technologies. And they have guests from different fields. Some of them are from our field, and like computational neuroscience, etc. So it's sometimes you learn theory, sometimes you learn application, or you have some people from machine learning, they compare Bayesian and they say, how do they apply Bayesian in machine learning, stuff like that. So that's all my talk. Thank you for your attention.